Hello everyone. My name is Mateusz Pusz. I'm doing C++ for a living for more than 10 years. Through all those 10 years, I did a lot of interviews, technical assessments from C++, and one of the things that bothers me the most is the lack of understanding of the tools we C++ developers use in our daily work. But by this understanding, I mean the trade-offs we have to accept when we are using such tools, especially the trade-offs in terms of the performance means. I have a good and a bad news for you today. So basically, the good news is that we have a lot of material to cover. That will be a pretty intense lesson today. Today we'll talk about shared pointer. It's one of the basic tools provided with C++11. It's used really in many different places. For the last 5 years, earlier it was used in Boost, and also was really popular. But before we go to this tool, I would like to ask you, why do we use C++? Of course, you could answer this way, that this is the best language ever, the most user-friendly, and the easiest to teach and learn. But I'm not sure if it's the right answer, or at least the most of you will answer that. I would say that we really use C++ because when it's used properly, it provides us the access to many low-level features, and we can do what we exactly want to do with our hardware. That's why the C++ motto is you don't pay for what you don't use, yes? So basically you have to opt in for some things if you want to use them, otherwise they don't bother you, especially from the performance point of view. With that, let's go to our smart pointers library that we obtained with C++11. We have a unique pointer that provides us the unique ownership semantics, and the shared pointer, the other one provided with C++11, and the subject for today's lesson speech. Björn Strostrup one day said that the C++ is the best language for garbage collection because it basically produces less garbage, and it's true. This is possible with the most important feature, I think, of C++, that is a destructor that allows us to create RAII pattern. I think that you already know what is a RAII pattern. It's a resource acquisition, it's initialization. It's more about the destruction than the construction, so the name may be a bit misleading, but it allows us to provide some actions when the object goes out of scope, and mostly it will be run with, the destructor will be run when you are going out of scope. There are some exceptions like abort, exit, jumps, and so on, but those are the exceptional cases for the control flow of the function and the scope. Basically, the RAII is implemented in that way. So you have some class resource that you are managing some resource. You have some handle to it in a private section. You have a constructor that obtains the ownership. It doesn't mean that it has to allocate it. It can just get it from somewhere else, like the smart pointers do. And you have a destructor that does all the magic. So basically, they reclaim the resource. What I find here is that one of the most important things that people don't remember is that smart pointers and RAII is not about memory only. It's not like a garbage collector for memory. It's for all the handles, all the resources we have in our computer. So it can be a mutex log, it can be a file handle, or any other thing you have to manage. Okay, so let's go to the shared pointer. Shared pointer is a smart pointer that provides us the shared semantics. And that means that more than one object, that the object may be managed by many shared pointers. It's being shared through our application. And as it is a RAII tool, shared object is destroyed together with the last shared pointer instance going out of scope or being assigned to. So basically, when I provide the interviews to new hires, I hear that it's a great tool because it makes us not only not worry about the destruction of the resources by ourselves, it also releases us from thinking about the ownership design in our application, because it just does its job, yes? It just covers all the bases We don't have to think about ownership. We don't have to think who is creating the resource, who is destroying it, how to pass it. It just works, yes? I wouldn't agree that it's a good idea. Resource ownership is one of the most important parts of the design of your software. You have to think about it from the very beginning, and you have to cover it through all the design stages. The question here is that if shared pointer ownership is a golden bullet just to cover all the bases and free your mind of the architect to think about it, or is a tool for lazy architects or designers that just want to make their application working right now and don't want to bother about it. There is a reason why Google C++ Style Guide say that you shouldn't design your code to use shared ownership without a very good reason. Okay, so our problem statement for today is a shared pointer. This tool seems to be really easy to use. It provides a really rich interface in terms of functionality, and it's really easy to use, this interface. That is why this shared pointer is too often overused by C++ programmers. What I mean by that it's overused, let's compare two simple examples here. We have two functions, foo and foo on the left and right side. They use basically shared pointer and unique pointer just to cover the ownership problem in our application. And what is the difference here? I'm not sure if you are familiar with Godbolt online compiler, but let's ask it for the difference on those two code snippets. So basically you have a function foo that has a unique pointer, and it produces us these assembly instructions. So basically you can see that there is an operator new called for the size of 4 bytes, and then it's an operator delete also for those 4 bytes. And that's reasonable, yes? This is exactly what you would expect using a smart pointer. This looks exactly like the code you would like by yourself, writing such a simple code snippet without the smart pointer. This is exactly what you would expect. There is no other more efficient way probably to do it. But let's change it to use the other case, so the shared pointer. See that? This is exactly what you will get using shared pointer in the same code snippet for the same use case. So basically to have simple resource acquisition is initialization wrapper around your memory. What we have here, we have some non-inline functions calling delete. We have some operator new, the same like it was earlier for the 4 bytes. We have another operator new for 24 bytes. What's more interesting here? We have some synchronized locking operations here. Going down, we have 2 more function calls. You can see it. You can see it here. This is a function call of the virtual method. So it's the dynamic dispatch being done here. The other function call is here. In fact, it's also a dynamic dispatch and virtual function call being done here. But GCC does a great job here to optimize and devirtualize this function. If you will lower the optimization level or use Clang, for example, you will see 2 virtual functions being called here because it seems that Clang right now is not that good in the virtualization of the application and the interfaces. Going lower, you see once again some synchronized instructions and some exception handling code. And also you will find some type info and vtable for our simple classes. So as you can see, it's much bigger than what you could expect looking into this simple code here. Basically, our question today and our task today is to describe what happened here. why this code is so much different than we could expect, and to raise the awareness where shared pointer should be really used and when you could just defer and use unique pointer or other tools by default. With my experience, I raised some theses that the best way to make people not use shared pointer too often is to make them write it by themselves at least once. It seems, at the very beginning, it seems that it's a pretty trivial task, but if you will try to dig in and to make the tool interface being 100% compatible with the ISO standard document, it turns out that it will take a lot of your time and efforts. Our goal today is not to implement everything because we don't have much time for it, but we'll try to implement the most interesting features and to describe them. The task is also to understand what happened in this assembly code I presented to you. And besides that, I hope that we'll be able to learn some new or interesting patterns that are being used in modern C++ currently, named things like empty base optimization or resource acquisition initialization, of course, and other idioms being used. And the other thing is that besides knowing how to implement them and to know how to name them, I hope that you will also try to think about them in terms of the cost they introduce to your application. So for example, if you will read about std function using things like type erasure, you would know what type erasure is and how it introduces the performance issues to your application, so you know the trade-offs, and you can either use it or not, because you will know what you can expect from it. Besides the code we'll present today, have some simplifications, of course, because slides are pretty short and we don't have much time to dig on all the details. And I must warn you, it will be pretty intense. So it's early morning. We are on the biggest and the best conference in Poland. So I hope you have a lot of power and will to dig with me in those details right now. So get ready. This is one of my favorite questions I ask on the interviews. So if you will ever want or you will have a chance to meet in the interviews at some company, you can expect I will ask for that, to prototype shared pointer. And these are the most popular answers at the very beginning where people try to implement shared pointer in a simple interview. Basically, both of those attempts are wrong, yes? The left one provides some issues when we have more than one shared pointer object pointing to the same shared owned resource. Because at the very beginning it seems that it works pretty fine, but if you have two objects, they tend to being out of sync pretty fast. The other solution people suggest is using static counter in our class. But this obviously shares the counter, but it shares among all the type instances, not the instances using or pointing to the same owned resource, yes? So the proper solution would be going with allocated counter on the heap. I would say that this is one of the best implementations I would expect from shared pointer, and if it was only for that, I would be really happy to have such tool in the standard library. I also can say that it probably covers about 90% of all the use cases you have in your applications, and it's pretty efficient in what it does. Unfortunately, it's not the case, and the truth is much more complicated. First of all, let's ask the question: is the shared pointer thread safe? Does it provide some thread safety guarantees or not? We'll have some simple examples here to show you what are the thread safety guarantees here. But for that, we will use a simple utility function. Run threads will create count number of threads, and will run a functor in those threads, provided as an argument to the function. Basically, it contains the container of futures storing integral value, and this as the container for our threads. We will initialize those threads with async tool, providing the unique identifier as a count minus minus to the functor, and then we'll obtain the result in another loop. So this is basically our simple tool we'll use here. And we have the first question. Basically, we are creating shared pointer here with the initial value 0, and pass it by a reference to our functor, and then we are assigning a new value to the stored object inside the shared pointer. Is it thread safe or not? What do you think? Who thinks that's thread safe? Raise your hand. Okay, who thinks that it's not thread safe? Okay, like 20% and 20%. So the rest are think that's yeah. It's not thread safe. Basically, shared pointer doesn't provide any guarantees to the usage of the object that is being stored in a shared pointer. It turns out that it's like a typical pointer or a reference. If you will pass any object to multi-threaded code by a reference or a pointer, you will have no thread safety guarantees, yes, if you will use them in different threads. And this is the same case here. We are just accessing this integral value 0 from different threads and assigning to it like it was a regular pointer. Using shared pointer here doesn't provide us nothing more. Okay, another example. We have once again, shared pointer created with initial value 0, and we pass it by copy to our functor. So each functor in each thread stores a copy of our shared pointer, and in our functor we assigned a new allocated memory, a new shared pointer, shared object to our shared pointer we store in the functors. Is it thread safe or not? Okay, once again, who thinks that is thread safe? Raise your hand. About 5%. And who thinks it's not thread safe? The same amount. Okay, this is thread safe. And basically, shared pointer is has synchronized state. So basically, you can access this state for different shared pointer instances in a thread safe manner. Here you are using different instances of the shared pointer because you have a copy inside the shared point inside the functor. Okay, so what will be here if you use a reference? So basically, this is exactly the same code, but we are using a reference to the make shared, to the shared pointer created with make shared. So basically, we are trying to reassign different shared objects to the same shared pointer created in a main thread. Is it thread safe or not? Once again, raise your hand. Who thinks it's a thread safe? Okay, who thinks it's not thread safe? Yeah, so you're right, basically. This is not thread safe because right now we are sharing the shared pointer instance. So basically we are reusing the same pointer in all the functors, and we are trying to modify it. So we have a writer. We are trying to modify the same shared pointer instance from all the threads, and it's not a thread safe. You have to provide additional synchronization primitives to access non-const methods of the shared pointer from different threads. So this is the last question here. This is a really similar example, but here we are using special overload of atomic store for the shared pointer to assign a new value to it. As you probably guess, this is thread safe. So this is this additional synchronization needed to modify the same shared pointer instance shared between threads. As a summary, all member functions of the shared pointer can be called from different threads when they touch different instances of the shared pointer, even if they point to the same stored object, shared object. So if you are working on different instances of shared pointer, you can use anything you want to modify that shared pointer. If you are referring to the same instance of the shared pointer object, you can use only const methods. If you're using non-const methods, you will have a data race. To not have the data race, you have some atomic overloads, as I presented to you. And the most important part here, shared pointer does not provide any thread safety guarantees on the object that is being managed by it, yes? So it's basically the same as rough pointer or rough reference shared between threads. No thread safety guarantees on this. You have to provide your own synchronization if you want to modify those data being stored in a shared pointer from different threads. All that magic of the synchronization in shared pointer state is done by atomic operations. And those atomic operations does not come for free. This is why you've seen those lock instructions in the assembly code, and they will be there even if you are running only single-threaded application, or even if you're running multi-threaded applications but never share data between threads. So you pay for them even if you are not using them. To make the implementation more complete, we can use atomic integral value introduced in C++11 as a counter. And this is some simplification to the real implementation, but for our purposes, it works correctly. It has a bit more overhead. And the lesson here is to remember to not pass shared pointer to some functions by copy if they are not about the ownership. So all the functions like print, like, I don't know, get or anything, so all the things that get it by const, or just want to access the shared data inside the shared pointer, don't have to be passed by the reference to the shared pointer. By a copy, sorry. Because this copy will always increment the atomic counter when the copy is created, and then will decrement it when the temporary is out of scope. I would really like to see something like this in a C++ standard. From my point of view, it's an idealistic implementation. It just stores a pointer to the shared object, and it has some templated type to do the counting. So basically, you can, with simple using aliases, you have some C++11, have a shared pointer that is a single-threaded, or a saved shared pointer that is a multi-threaded save. Or you can even, if you care about the memory footprint, and you know that you don't have much references, because in many cases it turns out that you have up to 10 references to the object, you can use shorter counter there. Unfortunately, it seems that we are even not close to finish our task right now. I think you know about the weak pointer. This is another smart pointer type introduced in C++11. A smart pointer, this smart pointer is non-unique reference, and to point to the non-unique reference, it has to be a shared pointer somewhere that was created. And this non-unique weak pointers, non-unique reference, points to the shared state created by the shared pointer. Weak pointer does not provide you the data themselves by the interface. You have to first create a shared pointer from it, and then get the interface. But in order to be able to create this shared pointer from weak pointer has to know everything about your shared pointer in order to be able to create it. It seems that the weak pointer is mostly used to cover some holes in your design, so to break circular loops, or to implement some caching mechanisms. And this is more robust, I think, usage of it. And it's a good place here to show the Herb Sutter's favorite 10-liner. This is a really simple, short code that Herb Sutter's provided some time ago as his favorite code snippet. Basically, what's being done here? We have some static map of the widgets that are being stored by the identifiers, and we have static matrix to make all this thread safe. We are locking this matrix for the operation, and in these two lines of code, all the magic happens. Basically, what we are doing here is we are verifying if our cache contains the ID we are looking for. If there is no such entry in the cache, a new entry is created, empty one, so an empty weak pointer will be created. Or if there was an ID inside our cache, we have a weak pointer that either points to the state or it's already outdated. And we know this basically from the log function. Log function of the weak pointer will return us the shared pointer instance, and the shared pointer instance will be either empty if it's either obsolete or there was no entry for the widget in our cache, or we have a shared pointer that is non-empty if it was in our cache and it's still valid. In case it's not valid, we are loading our widget from some database, assign it to our shared pointer we are returning, and assign it to our cache. So to create a weak pointer from the shared pointer. And then we are returning it. So in those few lines of this function, we see a lot of power of shared pointer, weak pointer, thread safety, and I would say it's a really, really nice snippet and a lot of things to learn from it. So how our weak pointer is implemented? Basically, you have to move our counter from shared pointer to our shared state. We also have to move our pointer to the shared object to the state, so the weak pointer will know about it. And moreover, we have to provide additional counter for weak pointer instances. So it seems like a bit of overhead comparing to the unique pointer already. So you have two atomic integers. You have a pointer in a shared state. I also introduced two functions here. One will be called when shared pointer is going out of scope, another one when weak pointer is going out of scope. Basically, when shared pointer goes out of scope, then the shared object is being, stored object is being destroyed, but we may not be allowed to destroy the state because the state has to live as long as at least one weak pointer lives. Weak pointer release, on the other side, has to verify if there is no shared pointers and this was the last weak pointer, and in such case, all the state can be destroyed. So how to implement it? We have our class state that is templatized by type T. We have two atomic integral counters. As we are creating the state always with the shared pointer, we are assigning value 1 at the very beginning to the shared counter, and as it's not created with the weak pointer, we are assigning 0. And also our pointer that is being stored is null pointer, but it will be overwritten in the first constructor being run. This state is used from the shared pointer and from the weak pointer. Yes? Okay, and we have those two functions to be implemented. First of them is shared release function that is being run when the shared pointer goes out of scope. Basically, it just decrements the shared counter and verify if it's 0. If it's 0, it means that was the last shared pointer, so we can delete our stored pointer inside. And then we have to verify if there are any weak pointer references pointing to this state. If there are none, we can delete the state itself. Weak release, on the other hand, is called when the weak pointer goes out of scope, so we are dereferencing the weak counter. If it's 0, so it means that it was the last weak pointer pointing to this object. And there are no shared pointers pointing to it also, we can delete the state, right? But we have an issue here. Do you see an issue? What may be an issue here? Basically, it's in that line. Remember that operations in our state are atomic, are thread safe. Is that operation thread safe? It uses atomics. Basically, we are using 2 atomic operations, but the operation as a whole is not atomic, yes, because it's consisted from 2 atomic operations, but itself is not atomic. How to fix it? There is a smart trick being done in all the implementations I've analyzed. It seems that the weak counter meaning looks like this. Basically, it's the number of weak pointers plus 1 if there is any shared pointer out there. It simplifies us a lot the weak release function, because we have to just check 1 weak counter that way. So when we are releasing the last weak pointer, it will be either 0 or 1 if there are any shared pointers pointing to it. And we'll know if we can release the state or not. We have to fix our shared release function too. Just instead of verifying if it's 0, we have to, with last shared pointer, we have to decrement the weak counter too. And that basically fixes our problem. And with this smart trick of modifying a bit the weak counter functionality, we added thread safety and less, in fact, comparisons to our if statement in weak release. Okay, so we covered somehow the thread safety guarantees of our shared pointer. We added some support for the weak pointer, but what else can our shared pointer hide inside? Do you remember that part of the code? This is virtual function being called. This is how it looks from the assembly perspective. What's really interesting here is that the compiler, if we will not be able to devirtualize our program, it will not know what functions will be run during the compilation time. It means that it cannot run the function by its name. Moreover, it cannot inline it when possible. And what's more interesting here is that you have to read a pointer to get the vtable. From vtable, you verify which function to run. It may turn out that this function is not in instruction cache. And then our application stalls and waits until the instruction cache will fill with the code to run. That is why dynamic dispatch can really hurt you when you are caring for performance. So why do we have to pay for virtual function calls every time we use shared pointer? Let's compare once again with unique pointer. This is how a unique pointer is being constructed, yes? It's a simple type. You just provide either default constructed unique pointer or provide some allocated memory to it, and it's okay. If you want to pass a deleter, you just provide the deleter in a type, and either you just use the default constructed one if it's stateless, or the default constructed one suits you, or if there is some untrivial state inside a deleter and you care about it, you can pass the instance of the deleter to our constructor, and it will be copied to our unique pointer, yes? This is how unique pointer works. Let's compare it to the shared pointer. All information here is stored in a type, yes? With shared pointer, it looks pretty similar. You have either default constructed or new memory being assigned. But look what happens when you are assigning a deleter to shared pointer. There is no information in a type about the deleter. What's even more interesting, you can also pass an allocator to it, and also do not provide any information in a type. Such things is called type erasure in C++. Type erasure is a technique to represent a variety of different types by type neutral, so type erased interface to such class. In C++, it's being implemented with virtual functions and dynamic dispatch. Basically, what it means is that you have some state base that has some virtual interface, and that virtual interface and the state base is, as you can see here, it's type erased. There's no T inside. It doesn't know what it stores. It knows only what can be done on them, on the things that is being stored. So it can either release a pointer or destroy the state. And then you inherit classes from it, like this templatized state with pointer, deleter, allocator, and implement specific release pointer and the destroy function that will work with them. For our convenience, I'll also introduce here two new classes, shared state and weak state, that just wraps the operations on the state base. So our shared pointer and weak pointer is much simpler, and just use shared state, weak state that manages all the polymorphism, and it's being hidden inside that class. I don't know if you've seen the shared parent presentation. Inheritance is the base class of evil, but it's basically a similar pattern here. So this is our state-based class with interface to handle all the shared pointer reference counting and the destruction. We have a shared state that just points to the state base. We have shared pointer that just contains, aggregates the shared state. The same with weak pointer. We have our state base that looks like it. You already know it. We have shared counter, weak counter, default constructor. We have shared release and weak release functions that we already implemented. We add a new virtual function code to it that will release our owned pointer. If you're adding any virtual function to it and we want to use this class in a polymorphic way, we of course have to add virtual destructor. And it's a really good pattern to make our all polymorphic base classes non-copyable and non-assignable, yes? And then we are inheriting our state from the base class. Right now we are just templatizing it by the pointer we are storing inside. Please note that this is a final class. And because it's a final class, it's why the GCC was able to devirtualize it, at least one of the calls. We are putting the pointer inside. So specific type we are storing, and it's being initialized in the constructor. And we are implementing the release pointer, the virtual function from the base class that just is able to delete our pointer instance because it here knows the type of the pointer being stored. As you remember, base class doesn't know anything about the T or PTR. Here we have all the information in a class type. Okay, so let's continue. We have our shared state that points to the state base, and we have to somehow initialize our state. So we have a few constructors there. One of them is a constructor that just gets the pointer from the shared pointer instance, and it assigns to the base a new state instance that is type aware, yes? So state base is type erased, state of PTR is type-aware child class of the state base. What's also really important here is that every time we write things like shared pointer, braces, new something, we know that it will be handled by the shared pointer, yes? It will be deleted by it. So in case our, for example, construction of the state will throw an exception, we have to take care about the pointer being passed to us. We have to make a try-catch statement here and delete p if something wrong happens, and we couldn't create shared pointer that will delete the pointer provided. That's why this exception handling code was visible in the assembly code I presented to you. We have to make sure that we delete the data provided by the user if something wrong happens. Okay, are you with me? So hold tight. It will be even better. Because right now we handled only the pointer type of the smart pointer. Right now we have to handle also the deleter and allocator types provided to the shared pointer. So to do it, we first have to learn a bit about the interfaces that are provided with C++11 to our deleters and allocators. Basically, deleters are really simple functors that just get the pointer to the data to be released and call a function to release. In our case, we'll just use delete on the pointer. And also there is a requirement for the unique pointer usage, and it's pretty handy for other use cases too, to provide a converting constructor that can convert my deleter of type T1 to the my deleter of type T2. So you can use the same deleter for different types and just convert from one to another. Especially it's being used by unique pointer if you have derived and the base class, and you want to delete one from the other. And custom allocator interface in C++11 was greatly simplified. Basically, it just has the value type being stored or managed by the allocator. We have an allocate function that just gives the number of instances to allocate. It's not the number of bytes, but number of instances of the type T. And deallocate with the pointer to deallocate and number of instances to deallocate. We also add this converting constructor to it to make it possible to create allocator from type T1 to type T2. Making allocator interface simpler came with a cost of learning. We have to learn also about allocation traits that were provided with C++11. This is some dark magic of template metaprogramming in C++11. If you want to learn some cool stuff, I really recommend you going and seeing how it's implemented in the standard library. We'll not go through it right now because it's out of time and scope of our presentation, but it's really cool programming. Basically, what it provides us is this gets the allocator class we create and does all the magic for us. So basically, it provides all the things that are not provided by the allocator itself. So it has to provide the value type from the allocator. It also has to provide the pointer type. And it will be either a pointer type created in an allocator if allocator has it in this implementation, or if it doesn't have any pointer type inside, it will be just a value type pointer provided by the allocator traits. We also have allocate and deallocate functions that simply just gets our allocator and all the arguments and pass them to the allocator. It has rebind alloc type def that basically what it does for us is this magic of converting constructors from one type to another. So you can have allocator of T1 and allocator of T2 constructed with it. And we have construct and destroy functions that we'll be using in our example today. There are also much more functions there. You can look into the API reference, but they will be not used by us today. what construct function does is basically it calls allocator instance construct function if it's provided. Otherwise, it just calls a placement new operation on it. And the same goes with destroy function. It will either call a destroy function from the allocator provided if it has one. And if the allocator doesn't have that method, it will just call the destructor of type T. So this is basically how it works. How it's implemented is another story. You are free, and I can encourage you to look how it's implemented. It's really, really fun. OK, so let's type erase our deleter and allocator. We're adding new types to our class and providing some default values for them to just defer to the defaults used by the standard library. So default delete and allocator. And we are providing allocator type in our state. And we are using this rebind alloc to do it. So basically what it does, it takes our allocator and it modifies it, the T of allocator, to our state, as you can see in the last statement there. So basically what we have, allocator type is our allocator of type state, not some T we don't know. And going back to our shared state, we have a shared state constructor that just calls new on the pointer. We have a deleter here that just calls the new state with the deleter. And the most interesting part here, when we have a deleter and allocator, we'll see it in the next slide. So basically, you have three constructors that create our state. First of them is using the defaults for deleter and allocator. Second one is using only the default for allocator. Third one is providing the data from the user for all the types. And this is how you have to implement it. First of all, you have to take care about the exception safety once again. We are getting our allocator type from the state. We are creating instance of our allocator. So basically here is being done this rebind allocation, this converting constructor that makes our allocator for our type of state. We are allocating a buffer, a memory for it with allocate function. It's assigned to the base pointer in our class. And then we are constructing the state in the buffer pointed by base. This code is, of course, oversimplified because if the constructor will throw, we will not delete the memory allocated line above. It has to provide some more exception safety guarantees. And we also have a destroy function here. If you remember, destroy function was implemented by this. So we had the short release, we have weak release for the weak pointer. They were deleting pointer or state, depending where we are in the flow. And we are just replacing those with release pointer and destroy of the state in our child classes. Continuing with the type erasure, we right now assume that we have some member functions to obtain the deleter and allocator instance from our state. And then the release pointer can be just implemented as using of deleter for the pointer. And destroy, first of all, has to get our allocator once again for the type, has to destroy the class, and has to deallocate the memory allocated. Is it intense enough for you? I told you it will be a pretty intense course. Hopefully it's the morning, so you have some time. And you are fresh. I just need some water. So yeah, hold tight. It's going to end soon, but you have to be with me for a few minutes more. So we have to implement those deleter and allocator functions. So right now what we have is the interface. We know about the types, we know about the functions, we know how to use them, but we didn't store the deleter and allocator instance in our state. We have to implement those getters and to store somewhere the deleter and allocator instance. Of course, we could do it the same like this pointer. We could just add new members to our state, like deleter member and allocator member, and they will be always there, taking some memory. Because what C++ says is that every member of a class has to increment the pointer of it, so if you will point to the member, the pointers cannot be the same when they are pointing to different members, yes? The problem is when the default deleter or the default allocator, that both are stateless, are being used, you will always pay for the size of it. That is why another really nice trick is being done here. It's called empty base optimization. And we'll see how easy, let's say, it is to use that trick in your tools that you will build. Empty base class optimization is being used in most allocator-aware classes, like containers, like std function, like shared pointer. So it's really popular in modern C++, and I believe you also will have some types in your libraries you use in your work where you could benefit from this pattern. So basically, to implement empty base optimization, let's create some helper structure. What it has is it has some use EBO Boolean flag that is true when our class is non-final, because we cannot inherit from the final class, yes, and when this class is empty, because this is where we care about empty base class optimization. So if it's empty, then we want to have it of size 0, not size at least 1, like mandated by the standard. We have two specializations for this. We have specialization for true, specialization for false. Specialization for true just inherits from the type T privately, and for the false have the member type T. It constructs from the constructor the types accordingly, and gets either the pointer to our structure or the pointer to the member in the getter. So this is pretty simple helper tool for us. To use it, we inherit privately using this EBO helper for deleter and for allocator. We have to pass different indices here because in case someone will be too smart and will provide one type that covers the allocator and deleter instance interface in one instance, and then we could have some problems. So we have the same type for deleter and allocator, because that class may provide two interfaces in one class. So to make it distinct classes, we have to provide some additional index here. So we are doing some using aliases here to make it easier to use them. So we have dbase for the deleter base, we have abase for the allocator base, and we create our state for the pointer, deleter, and allocator. So what we do here, we basically initialize the dbase class, the abase class, and we assign the pointer to our member. And we provide two other constructors that just reuse the constructor with all the members and pass the defaults, if not provided by the user. And the last thing here is to provide those delete and allocator getters that just statically cast our multiple inherited class to specific base class and call get on it to get the data stored there. So either it will be the member inside the EBO helper class or the base class of it, depending on the implementation. Okay, so we are approaching the end of those hardcore template metaprogramming stuff here. But we have to cover two more things. This is the design with which we ended right now. We have shared pointer, we have shared state, we have a state base that provides us the virtual interface to our state that knows everything about our type. And you have an issue here. It seems that it's really expensive to get the PTR instance. If you would like to get it, and this is the most often used operation on the shared pointer, yes, just to dereference it to get the pointer being stored, you would have to probably provide additional virtual function to the state base and get the T somehow and provide it to the user every time. So another dynamic dispatch every time you want to dereference shared pointer. It's not effective, yes? That's why it was decided to optimize the performance on the cost of the memory footprint and provide another T inside our hierarchy. So we have basically two pointers being used here. One of them is stored inside the shared pointer. Another one is owned by the shared pointer. One of them is put in the very high in this hierarchy, and it's being provided by the getter, by the get method, or the dereferencing operations. And another one is stored and is owned by the state, and is being used and released when the shared pointer goes out of scope. So to implement this, it's pretty simple. We just have to add pointer to our state. We already had it, and we have to add another pointer to our shared pointer class. There are some advantages of such design. Besides, we have some disadvantages, namely saying about the memory footprint. Let's consider such simple example. You have a class A, some structure A, structure B, one of it inherits from the other, and you have virtual destructor in one of them and regular destructor in a second one. And we create shared pointer of type B and create B. We create shared pointer of type A and create B. And basically, shared pointer will still know how to destruct B in that case because it will have B in the state, and only A will be used in our shared pointer instance. And the same if you will move from one place to another. The difference is when you compare it with unique pointer. Unique pointer will have some issues here. Basically, unique pointer will behave the same as you would work with typical pointers here. So basically, if you are using polymorphic base class, it has to have virtual destructor in order to know how to destruct the class by its base pointer, yes? Unique pointer stores only one type, and it doesn't know what is the type when you cast it to the base class. So be aware of it and know how to use that trick. On the other hand, I don't think it's that useful and that good pattern to have class usage in polymorphic way without a virtual destructor, but it somehow works, and in some cases it may prove to you. Okay, but we have another trick with shared pointer. Do you know that you can do things like that with shared pointer? You have shared pointer of class A that has some integral data inside, and you can create a shared pointer of int, passing this S1 instance and pointing to the integral inside. Or in fact, any other type and variable even on the stack. And the typical usage of this is that right away you can reset S1, making the use count equals 1, and you can move it to some interface that wants shared pointer from int from you, not the shared pointer of A that you constructed. That thing is called aliasing constructor in shared pointer. And it basically looks like this. It takes the reference to the shared pointer of different type and another type pointer provided as a second argument. What it provides us is just allows us to set those two different pointers in our hierarchy, this very high and this very low pointer, to two different totally types and instances. You have the control what they point to. The important part here to see is that the stored pointer is not deleted by the shared pointer, yes? Only the pointer stored in our state will be deleted. So you have to make sure that things that you will pass as a second argument to this constructor will live at least as long as the object that you are owning, because otherwise you would have a dangling pointer and you will have some issues. Side effects of it is that you can create an empty shared pointer with non-null store pointer, or you can create non-empty shared pointer that stores null pointer. I don't know what are the use cases for the second case, especially. It can be something like you have some secret stuff that no one can touch, but it has to live somehow and maybe do some magic in the destructor or something. And the first case may be used as a, for example, replacement of the shared pointer with empty deleter. So basically, if you want to, pass something to the interface that just requires you to provide a shared pointer, but you want to point to the things that are static or a stack, that delete will not be possible on it. So this was the aliasing constructor, and the last feature that is really popular and everyone says to use it is a make shared, yes? Together with make shared, we have an allocate shared function that I don't know if you are aware of. It's pretty similar to the make shared, and it basically constructs an object of type T and wraps it in a shared pointer. What's the most important point here is that ISO standards require us to do at most one dynamic allocation here. So this is basically as efficient as intrusive smart pointer that we don't have in the standard library itself. But basically with make shared and allocate shared, it is as efficient as intrusive pointer. How it works? This is what we have right now, yes? We have two dynamic allocations. One allocation is of type T, another one is of our state. And you have two pointers, pointing to T from the shared pointer and pointing to T from the state. With make shared and allocate shared, we create such a stuff. Basically, we are creating one big buffer that contains both the state and type T itself. So it's like size of those two types, yes? Plus some maybe padding. And what's even more interesting here is that we have only one T pointer here. So we save some space. We don't need to provide additional pointer like it was on the case on the left side. So our state in place will be smaller and plus shared pointer than the solution on the left side. To implement it, we create another state named state in place that just also inherits from state base and puts some allocator to the EBO. We create a buffer for our type T that is of proper size, a proper alignment to store our type. We also provide some getter that will get our T from the buffer. And we modify our release pointer and destroy virtual functions to properly destroy this and construct this. What's interesting here, because we have a buffer here, we don't need another T pointer here to know where the object is, because we know where it lives. If you've seen Stefan Lavavier's presentation from a few years from Going Native, he exactly described that optimization there. Also, what's interesting here is that release pointer will be called when the last shared pointer is going out of scope, yes? So the object will be destroyed, but the memory created for the state cannot be released as long as at least one weak pointer is out there, because it has to know the state. And the state right now is of size of state and the type. So basically, if you are owning huge types inside a shared pointer, and you are using this with this, for example, caching snippet I shown you from help SUTTER'S, it may turn out that your cache is outdated, not used anymore, but it still has a lot of memory allocated. And in fact, the data is not there, but the memory is still kept to make the state right and being proper. And with that, we made it. We implemented our shared pointer. I know that it was pretty intense, and we had a lot of code being shown here. If someone got lost, I recommend you looking into this offline when will be available the video from this. And as the last point here, I would like you to just see some simple anti-patterns to learn from this. Basically, what we learned is that passing shared pointer as a copy is a really bad idea here. Yes, because of the atomic operations being done there. If you have simple getter or printer, better pass a reference or just reference to the stored data instead of the copy of the shared pointer. Another anti-pattern that is pretty popular is that people tend to use to create shared pointer from or more than one instance of the shared pointer with the same allocated memory. It may be presented this way or this way, that you can call get and create another shared pointer. Basically, it will do double delete or call double deleter twice if it's not be default delete. So basically going to undefined behavior length. So do not create many instances of the shared pointer from the same allocated pointer. And the next anti-pattern here is to use new explicitly, especially in that case in a function call. Consider what happens if bool will throw exception. In such a case, this things that was allocated by new, maybe earlier by the compiler, let's say, may never end up to our shared pointer, so it will never end up to our try-catch clause in this constructor, and may never be deleted. So basically, you should just use make shared for things like that, or allocate the pointer above, for example, shared pointer before calling the function foo. I think that the last anti-pattern I wanted to present to you is the is that, yes, do not explicitly delete the pointer stored by the smart pointers. It may look trivial here, but if you have a complicated application that you once use shared pointers, otherwise you use pointers, just dereference from it and spread it across your application, it may turn out that it will end up in a deleter somewhere. Be aware of it, yes? And the best practice is just do not use delete and new expressions at all in your code. We are writing modern C++ from C++ 11 and 14 when make unique joined the team here. We don't have to write new and delete nearly anywhere in our code. Okay, so let's go back to our C++ motto. You don't pay for what you don't use. And see how it works for our shared pointer class. Let's define our feature overhead definition here. Is that it's something that you have to pay where you are not using in your code. And here's the list of features that are used by our shared pointer implementation. We have RAII, yes, resource acquisition is initialization. Is it overhead or not? I would say it's no overhead. If you would like to write similar code by hand, it will be pretty the same behavior. And you are using smart pointers to use RAII. Reference counting. It's an overhead, of course. If you can just using the smart pointer that you could use unique pointer, like in the first example we analyzed, reference counting is with the cost, yes? Thread safety, it's with the cost. Empty base optimization, is it a cost or not? No, it isn't, yes? It even makes our memory footprint lower. So it's an optimization, not the overhead. Weak pointer support comes with a cost, yes? You have additional pointer being stored. Additional counter, sorry. Type erasure comes with the cost of the dynamic dispatch, yes? Custom allocator deleter support that we analyzed. I would say because it's empty base optimization, it doesn't provide you any additional cost here. All those functions, allocate, deallocate, even allocator traits tend to be inlined pretty nice by all the compilers, and there is no function call overhead whatsoever. Aliasing constructor, well, maybe. In this case, it was for free because we had those 2 pointers already there, so we could use them in a different way. But if you would not have, for example, the weak pointer, and because of this, you would have no additional pointer in the state, or you have no type erasure, sorry, maybe more important here, then you would have to pay for the rational pointer if you would like to have aliasing constructor without type erasure. Make shared support doesn't provide you any overhead, considering this small exception with the buffer being bigger. So, when the shared pointer is optimal tool for you? First, your application has to have shared ownership in your design. Second, you have to use more than one thread, and you have to share the data pointed by the shared pointer between them. 3, you have to use weak pointer, for example, to break cycles. In the writing of the application, you don't know which allocators and deleters will be provided to your shared pointer instance at any time. So they will be runtime determined, and you use type erasure. You are using aliasing constructor. If all of those cases are covered at the same time in your application, then shared pointer is an optimal tool for you. Is there any application in your work or in your, I don't know, open source activity that you are using all of those cases at the same time? Probably not, yes? If not, you pay for what you don't use. And that's what bothers me with the shared pointer. That's why I would say we should be really aware of what it does and why we pay and what we pay for using it. So here are some quotes from the community. Herb Sutter said, prefer unique pointer. Sean Middletwich said that shared pointer is best avoided in any production bigger software. Shared pointer is as good as a global variable by Sean Parent, yes? And I like this quote the best. It's a really cool library. You can learn from it a lot, but you shouldn't use it. With that, I finish. I have probably about 2 minutes for questions. Are there any questions about this? I know it was pretty intense. Sorry, but it was my intent to show you all of the stuff so you know what you are using.
So we have class A, class B, B extends A, and we, let's say we have a function.
Do you remember?
This is this example. And so if you've got function which expects unique pointer specialized by A, so you cannot pass the unique pointer specialized by B, because it can be done for the shared pointer.
Yeah, you can pass it, yes. You can pass it because, for example, the unique pointer has a converting constructor, so it will convert from B to A because these types are convertible to each other. But when unique pointer will be destructed, you will call a destructor of A. And destructor of A is not virtual, so it will not call the destructor of B, and you will have a lot of problems with that. So basically it will compile, yes, fine, but will not work.
I need to recheck it, because I knew that it will be working for the shared pointer, but I also hope that it will be working for the unique pointer.
No, without the virtual destructor, it cannot work. Like you will have a typical pointer or a reference to the base class. You cannot delete it with a pointer without a virtual destructor.
So thanks for suggestion, and I will recheck.
Okay.
I have a question. So what would you recommend instead of using shared pointer if you need to use at least a few features that were listed at the end of? Would it be a unique pointer with some special implementation around it, or something different?
If I need a shared pointer semantics in my code and I don't want to pay for any other things, I would probably write something like this. It should be pretty easy exercise with such an interface. Yeah, with that, thank you very much. I don't have much more time for the questions. If you have more questions, you can find me on the break. Thank you.